right, welcome to this part of today's lecture. Again, this is just going to be an example showing what we can do with Bohr's model. Again, it makes some pretty big assumptions that we can do stuff, but we're going to go ahead and try it. All right, so here we have the question I gave my class. So it's for hydrogen and ionized lithium. The lithium is ionized to the point where it is able to be used for Bohr's model. Also, I explicitly told them to use it for Bohr's model. So I told them they had to show work in order to get points because this is a yes or no question. But the why or why not part meant they needed to show work. So I just want to kind of explain that. So they weren't explicitly given the energies. In this case, they had to go through and calculate them. So for A, we are dropping from an excited state to the ground state. So in part A, we are trying to find the wavelength. So we have hc over the change in energy, where that change in energy is going to be energy 3 minus energy 1. So we need to calculate those energies first. The energy of hydrogen is given by negative 13.6 eV divided by the n squared value. So that meant that for E3, we're going to have negative 13.6 divided by 9. And for the ground state, we're just going to have negative 13.6 eV divided by 1. So for these values, right, you just plug them into a calculator. You're going to get the value. So this is negative 1.5. It's 1 repeating. I just had, I think when I did the calculation, I carried all my digits, but let's just write out 3 ones. That's plenty. This is in electron volts, minus 13.6 electron volts. So here we are going to end up with a positive value. So we're going to have the wavelength. We need to use Planck's constant. Again, we want to use Planck's constant that is in electron volts. So that value was 4.14. Didn't give myself enough space. 4.14 times 10 to the negative 15 electron volts times seconds times our speed of light, 3 times 10 to the 8 meters per second, divided by our change in energy. So again, we had negative 1.5111 electron volts minus negative 13.6 electron volts. Taking this and plugging it in, I got 1.02739 times 10 to the negative 7 meters. So my wavelength is going to be 103 nanometers. So this is going to be the wavelength of light that is emitted by the hydrogen as it goes from n is equal to 3 for n is equal to 1. So this is our answer for part A. In B, we have the situation of where we need to calculate the we need to see if this wavelength can be absorbed by lithium. So in order to do that, we're going to need an equation that we haven't seen in this class. So the energy for lithium, turns out, can be calculated by negative 13.6 eV times Z squared over N squared, where Z here is the number of protons inside of our nucleus. Basically, it's our atomic number. For lithium, that is 3. So that means that we can multiply negative 13.6 times 9, 122.4 electron volts divided by N squared. So now we have the ground state energy for lithium. So let's look at our equation again for the wavelength. It's equal to Planck's constant times c, the upper case minus the lower case, which in this case, our electron is starting in the ground state. So I need to go through and calculate the energy of the upper state. So this is something we had done in my Physics 121 class a couple of times. I haven't checked every question in this textbook. I know there is one similar to this in what you are doing, but it does part A for you and you're just doing part B. So if I can calculate my upper energy level value, and I'm not going to solve for that explicitly. What I really want to solve for is the N value for the wavelength of 103 nanometers. This is what I actually want to do, because if N is equal to 2, that means that my electron is in that energy state. So if N is equal to 3, 4, 5, that is the state I'm in. In order to solve for N, I need to calculate the energy level that would exist if it absorbed a wavelength of 103 nanometers. So that is what I am doing. I'm going to solve for this upper energy level. I don't know what it is. I'm going to use that, solve for N, and then once I have that, I can go through and say, well, if this is what N is, then I absorb it. If N is a non-whole number or a negative number somehow, that indicates to me that this wavelength cannot be absorbed. So N has to be equal to a nice positive integer value. So rearranging my equation to find the upper energy level, I would have Planck's constant divided by times the speed of light divided by the wavelength plus the ground state of my energy level. So I'm going to be dealing with everything in terms of electron volts, so 4.14 times 10 to the negative 15 eV times seconds, 3 times 10 to the 8 meters per second, divided by the wavelength. For best practice, we should use the extra sig fig. So because light is in meters, I need to use my value in meters. So I think it's 7.4 times 10 to the negative 7 meters, plus the energy level for my ground state, which is 122.4 eV. So I'm going to go through, and I now need to plug all of this, into the calculator. Something I noticed a lot that happened for students is that they would forget the power here. And what that happens is they would use this in nanometers, but this wouldn't be in nanometers, so make sure units match up. So the upper energy level that I got was 101.311 electron volts. So again, I need to make sure that my upper energy level is going to be equal to negative 122.4 eV divided by N squared. N has to be equal to a whole number. So I'm just going to take my ground state divided by my new value that my electron would have. So if I do this, I am going to get a positive number because both of my energies are negative. I'm going to have to take the square root of that. And I found that my ground state, or sorry, my N value is 1.0533. It's unitless. This is not equal to a whole number. It's not even close to 2. So because my state number is not an integer, this would, even if it was, the closest integer is 1, I'm not going to even leave my ground state. So this tells me that my lithium would not be able to absorb that particular emission from hydrogen. So if our gas has hydrogen and lithium, from going from the excited state of n equals 3 to 1, I'm going to emit a wavelength of about 103 nanometers. My ionized lithium is not going to be able to absorb it, and that particular wavelength would just pass straight through. So this is something that is useful for Bohr's model. It can help us start figuring out what wavelengths objects can and can't absorb, assuming you have something a little bit more complicated where you have a compound gas. You start having multiple elements inside of your gas. But again, it uses the assumption that our electron is only 1, which for a lot of elements isn't possible, which is why Bohr's model isn't, I mean, it's obviously used for an educational tool, but once you start getting into quantum mechanics, it's not the best model, but it is a good basis for then building up quantum because it should agree with the Bohr model information, especially for hydrogen. All right, so that's going to wrap it up for this lecture. And again, congratulations on making it through all the new material. From here on out, it's just review for the final. So that's that. If you have any questions, please ask. And if you haven't taken the lecture quiz, be sure to do so.